Hello everyone, welcome to Math 1325 Exam 2 review. My name is Kari and I will be leading the review today, so we'll go ahead and get started. If you have any questions during the review, make sure to drop them in the chat and someone will help answer them. And with that, we'll just get started. So our agenda for today is going through all these different topics. These are your topics on your exam 2 that you'll be tested on. So if you guys want, you can take a picture of it or a screenshot of it. I'll just wait a few seconds so that you can do so. Alrighty, we'll go ahead to our very first topic, which is differentiation using basic rules. So on the right, you can see 9 rules that you can use when you're given a function to differentiate. So some of the main ones are taking the derivative of a constant. So when you're taking the derivative of a constant, it's always going to be 0. Wait, also, if no one can hear me, please go ahead and unmute yourself. I cannot see the chat or hear the notifications. So if there's ever you cannot hear me or if there's any kind of problem on my end, please unmute yourself and let me know. Moving on, the power rule. So number 5 here talks about power rule. So you'll see that you would take the very first term as it is, and then whatever it's multiplied by, you will take the derivative of that, and then you will add it to the second term multiplied by the derivative of the first. However, if you look at the quotient rule, you will notice that it's the same, but instead it's subtracted and divided by the denominator squared. Something to keep in mind between the product rule and the quotient rule is that in product rule, the order does not matter. But in the quotient rule, the order does matter because it's subtracted. You always have to do the derivative of the numerator times the denominator subtracted from the derivative of the denominator times the numerator. You cannot change the order here. Another thing we'll go over is the power rule. The power rule is basically your basic differentiation rule. So it's basically taking the power down. For let's look at number 2 here, the second rule. So it's basically taking the power down and then subtracting the exponent by 1. And then that is your power rule, basically. So another one that we want to look at here is chain rule. You would use chain rule when you have a composite function. That means a function embedded within a function. So when using chain rule, we'll look here at number 7. So when using chain rule, you'll take the derivative of the outside function using power rule, and then you'll take the derivative of the inside function and multiply it by the derivative of the outside function. So if you have any questions, again, drop them in the chat. Moving on to derivative using log rules. So when you're using log rules, you would just use your logarithmic properties to first simplify the function. So when you see ln or log, so if you see natural log or log, that's when you will simplify the function first and then take the derivative of it so that it's easier. For example, here you would have to do chain rule, composite rule, all these, chain rule, product rule. But if you simplify it down, you'll realize that you will not have to do any of those rules. So, and it's just going to be a simple differentiation. Something to keep in mind is that after you simplify the function, you've not yet found the derivative. A lot of students, what mistake they make is that they just simplify the function using logarithmic properties, but never actually differentiate it. So make sure that you're simplifying it and then you're finding the derivative of it and not just simplifying it and leaving it as your final answer. So let's take a look at this example here. So here we have natural log of 7x times 3x plus 5, 3x squared plus 1 to the exponent of 5. So the first rule that we would apply here is number 1, right? You see it's multiplied. So you can separate it and you can do ln of 7 plus ln x plus ln of 3x plus 5. You can't break down the 3 and the x and the 5. You see how they're all in parentheses, so you can't really break it down like that. This way you did it with 7 and x. There's no parentheses around 7 and x, so you can do ln 7 plus ln x. And then you would use the third log rule here for 3x squared plus 1 to the power of 5, and bring the 5 in the front of ln, and then you'd multiply it by 3x squared plus 1. And now you can go ahead and find the derivative of this, and then you'll end up with this as your final answer. So again, keep in mind that first you simplify using log rules, and then you still have to find the derivative. Simplifying it using log rules is not your final answer. So next we'll go into linear inequalities and nonlinear inequalities. Can someone come off of mute and tell me what the difference between a linear and nonlinear inequality is? Okay, that is all right. Linear inequalities are basically just your functions that don't have any kind of like exponents in it, and nonlinear is like when you have x squared plus 1 or 3x cubed plus x squared. So anything other than a linear equation is nonlinear. That's where you have like exponents and you have like powers. So when you're doing linear inequalities, these are like the steps that you would follow. So you would add negative b from both sides of the equation. So we're referring to this equation. So you would solve it as you would solve any linear equation, but instead this is an inequality. So if you subtract negative, or if you add negative b to both sides of the equation, you'll get ax is equal to c minus b. And then you would divide both sides by a, and then if your a is greater than 0, you'll get x is less than or equal to c minus b divided by a. But if it's less than 0, you'll get greater than c minus b divided by a. So if your a is less than 0, that means it's negative. So when you're like dividing by a negative number, always make sure to flip your inequalities. So that's something to keep in mind as you solve that. Now let's look at this example. So we have here 2p minus 5 greater than or equal to 11. So if 2p was 2p squared, this would be a nonlinear inequality. But since there's no like to the power 2, to the power 3, 4, or anything, this is a linear inequality. So the first thing you would do is you would add negative b on both sides. If you do negative b here, it would be positive 5. So if you add that on both sides, you'll get 2p is greater than or equal to 16. And then you will divide both sides by 2, which is your a. And since a is greater than 0, you will not have to flip the inequality. So you get p is greater than or equal to a. Now you would use a number line to like see what your answer would be. Since it's greater than or equal to, you will have a solid dot at 8. And since it's greater than, your arrow will be going to infinity. And since, again, it's greater than or equal to, you'll have a hard bracket around 8 when you're writing your solution, but then you'll just have a parentheses around infinity. But if it was just greater than, then you would have an open circle here at 8, and you would just have parentheses, not a bracket, before 8. So if you have, again, any questions, make sure to drop them in the chat. And then moving on to nonlinear inequalities. So these are the steps to solve through a nonlinear inequality. I'll actually jump to the example and kind of walk through these steps instead of like trying to like solve them. I'm going to explain this. So our question here is 2x minus 8 divided by x squared minus 4. Do you see this x squared here? That is what makes this a nonlinear inequality. So the first thing we need to do is find the cut points of the function. So to do so, we'll set the numerator and the denominator equal to 0. And when we solve that, we get x is equal to -2, 2, and 4. Then we would make a sign chart. So we just put those numbers on the number line, and then we take a number before or like in between two numbers and plug it into the original equation, and then determine if that's a negative number or a positive number. So here, if we plug in -3, it's negative. The answer would be negative, so it'd be a negative and then a positive, and you would do so. And then now you would see on what intervals is it positive. So it's positive from -2 to 2, and then it's positive from 4 to infinity. Then you'd do the same with where it's negative. And then you would move on to solve for if it's less than or equal to 0. And then that's when you would see that from -infinity to -2, it's less than or equal to 0. And from 2 to 4, it's less than or equal to 0. And since it's less than or equal to 0, you would have a hard bracket around 4. And with that, we will move on to increasing and decreasing intervals. So I know this is a lot of words, but I will definitely simplify it down. So increasing function. So when you're looking at a graph, when you're moving from the left to the right, and you observe the graph, and if the values are increasing, like when you're moving through your x values, if your y values are increasing, that means the function is increasing. But then if you see that the y values are decreasing, that means it's a decreasing function. So that's kind of all you need to know here. And then we'll go into relative min or max. So a local maximum is when f of, so it's at any point where it's a higher y value, and then the minimum is like when it's a lower y value. So when you're looking at the graph and you're walking through the graph, you will know relatively if it's a minimum or a maximum. And then we'll use the first derivative test to also test and see if a given x value or like a given critical point is a minimum or a maximum. So let's move on to like this graph and see. So first thing it asks for is the domain of the function. So the domain of the function is -infinity to +infinity. You see the graph just keeps on continuing on both sides. So it is a continuous function, and it just like never stops. So it's from -infinity to +infinity. So we need to provide all the cut points of f prime x. So the cut points are basically your critical points. So those will be where there's a maximum or a minimum on your original function. So here you see there's a max at -2. So -2 is one of your cut points. It's not where the graph intersects with the x values. Like it's not the point right here or the point here. It's where the original function has a max or a min. So you'll see at 0 there's a minimum. So that's another cut point. And then at 2 there's a maximum, and then at 3 there's a minimum. So you'll see all these different x values or your cut points. Oh, sorry. And then you want to see at what intervals is the function increasing. So you'll see that from -infinity to -2, it's increasing. As you're moving to the right, your y values are increasing. and then it's decreasing, and then it's decreasing from -2 to 0, and it's increasing from 0 to 2, and then decreasing from 2 to 3, and then increasing from 3 to infinity. So we kind of answered both those questions there. So now we want to find all the relative minimums. So we already established that at 0 there's a minimum, and your y value here is -2. And then at 3, 2 here, that's another minimum. And then your maximums are at -2, 8, and then 2, 3. Let's move on to looking at how to do a first derivative test. So this is our function right here. So to find the critical points, we would find the derivative of the function and then set it equal to 0. And when you set it equal to 0, you will see that the function has critical points at x equals 0, 2, and -2. That means these are the x values at which the original function has a minimum or a maximum. And then we would make a sign chart. So basically how we did with nonlinear equations, we just make a sign chart, plot those numbers on the line, and then we just find a number in between and kind of plug it into the original. Okay, here you would not be plugging it into the original. You would plug it into the first derivative, and hence it's called the first derivative test. So you plug it into the first derivative, and then you will see if it's negative or positive. Make sure you do not get those confused between nonlinear and first derivative test, just like I got confused right now. So the intervals on which it is increasing would be from -2 to 0, and then 2 to infinity. And then it's decreasing from -infinity to -2, and 0 to 2. And then now we're going to make a slope chart. So basically, if you see that it's decreasing, you just draw a line going down, and if it's increasing, you just draw a line going up. So based on the slope chart, you'll know where there's a maximum and where there's a minimum. So after that, when you want to find the y values of the cut points, or like where there's a maximum or minimum, so let's say if we see that there's a maximum at x equals 0, make sure you plug the 0 into the original function, and then you'll get 1. Don't plug it into your first derivative. You plug the numbers in between your critical points into the first derivative to see if the function is decreasing or increasing. But when you want to find the y value, like the actual point for where there's a maximum or a minimum, you will take the x value, which is your critical point, and plug it into your original equation, and then you will see where there's a maximum or a minimum. And then we will move on to higher order derivatives. So higher order derivatives are basically just like differentiating the function until you can keep going, right? So you know that there is like the first order derivative, and then the second derivative, the third derivative, fourth, and so on. So you can just keep on differentiating. There's a point when you will like hit 0 most of the times, usually by the fourth derivative, but if it's not 0, you just keep on going and going. So if you want to take the second derivative of a function, you have to take the first derivative and then take the second derivative. There's no shortcut to just directly taking the second derivative of the function. So to take the second derivative, you'll use the first. To take the third, you'll use the second, and so forth. So if on the exam they ask you to find the sixth derivative, then you need to take the first, the second, the third, the fourth, and the fifth, and then using the fifth, you'll be able to find the sixth derivative. And then we will move on to concavity and inflection points. So on the left here, I have like the steps to go through concavity and how I like to find the inflection points. And then we'll look on the example at the right. So the first thing that you'll do is you'll find the second derivative and set it equal to 0 to find the x value of the point of inflection. So here when you have to find the second derivative, you'll first have to find this first derivative, and then you'll find the second derivative, and then you'll set it equal to 0. And then you need to find the x value of point of inflection. So when you set it equal to 0, the value that you get is not a critical point or a cut point. It is just the value for your point of inflection. And your point of inflection is where your graph changes concavity. So, and then you will use the number, like just like you would do like a sign chart, and then this time you will plug it in to the second derivative, and then you will see if it's greater than 0 or less than 0. So if it's greater than 0 when you plug it in, that means it's concave up. Otherwise, it's concave down. So let's look at the example on the right. So we have this function up here. The first thing we do is find the first derivative. Then we go find the second derivative. And then we'll set that equal to 0, and then we get x is equal to -1. So now you'll go back. So here's like your work for how when you set the second derivative equal to 0, you get -1. So remember, this is not a cut point or a critical point. It's just an x value for the point of inflection. So you make a sign chart, you plot it, and then you take a number less than -1. And then when you plug it into the second derivative, you get less than 0. So it'd be concave down. And then when you plug it into your second derivative, like a number greater than -1, like 0 or something, then it is concave up. So your intervals for the solution would be from -infinity to -1, the function is concave down, and then from -1 to infinity, your function is concave up. So now to find the point of inflection, right? So you know that -1 is your x value. So you will plug this in to the original equation, and then you'll get 15 for your y value of the point of inflection. Remember to always plug your cut points, critical points, like your x values for point of inflection, into the original function to find the y values. And then we'll move on to your second derivative test, which is our last topic. So the first step that you will take is you will find the first derivative, set it equal to 0, and you want to find the critical points or the cut points. And then in your step 2, you will plug those critical numbers, only those that are within the domain, into the second derivative to determine if there's a local max or a local min. Right? So here you don't have to do a sign chart or anything, but you do need to find your first derivative, you need to find your second derivative. So you set your first derivative equal to 0, you get a few x values. Now you plug each one of them into your second derivative, and then you will see if it's greater than 0, that means there's a minimum. But if it's less than 0, then it's a maximum. And if it's equal to 0, then it does not exist. And make sure that critical number or your cut point is within the domain. And this applies to your first derivative test as well. And then to find the y values of the critical point, plug the critical number back into the original function. This is something we've been talking about. So let's look at this example. So here we have the function, and we find the critical points and then see if there's a local maximum using the second derivative test. So the first thing we do is you will set that equal, we will find the first derivative, set that equal to 0, and then we find points -3 and 1. And then we see that we take the second derivative of the function. And now we take the critical points or the cut points and plug that into our second derivative. And then here we get -12 for -3, which is less than 0. which means there's a local max. And then when we plug in +1, you get +12, which is greater than 0. So that means there's a local minimum. So now you will take -3 and 1, plug it back into the original equation, and then you'll get 31 and -1. So you have a local max at x equals -3, and then a local minimum at x equals -1. So the points would be -3, 31, and then 1, -1. So that concludes our review portion. Alrighty, we will get started with our practice problems portion. So since there's only 2 of you guys, we will not be using the breakout rooms. And I will hand it over to Luke now to lead you guys over the practice problems.
Okay, so this first one right here, differentiate using derivative using the differentiation rules. So we want f prime. This will be the answer. So f is a function raised to some power divided by a function raised to some power. So since we're dividing, can you guys hear me all right?
Yes.
Cool. Since we're dividing, we're going to need the quotient rule. And since we have these powers up here, they will be, that will cause us to use, we'll have to use the chain rule. So I'll write the quotient rule. And the chain rule. We need these to do this problem. So the quotient rule is saying, like, if we want the derivative of these are f, so I'll use u and v. So we want the derivative of this. This is the prime notation. This means derivative. This is just the quotient rule that was in the slides. This was, I remember it, low d high minus high d low over the square of what's below. And then the chain rule, if we have like some function g of like u, and u is a function of x, and we want to take the derivative, then this would be u prime g prime of u. So I remember this one as take the derivative of the outside and leave the inside alone, and multiply by the derivative of the inside. So we need both of these rules to do this derivative. So if we have f of x is 3x plus 5 to the 5th over x squared plus 2 to the 50th, then we can calculate f prime. F prime is low d high, And to do d high, we need the chain rule. And so d high would be the derivative of 3x plus 5 to the fifth, and then we're taking the derivative of this. This is equal to, take the derivative of the outside function. The outside function is just something raised to the fifth. So we're going to take the 5, we're going to use the power rule right here. 3x plus 5 to the fourth. And then multiply by the derivative of the inside. I put that right here in the statement of the chain rule. So then we multiply by 3, because the derivative of 3x plus 5, well, the derivative of 5 is just 0. We know that because that's a constant. And then the derivative of 3x is just 3. Whenever we take the derivative of something linear, it's just the slope. So this is the derivative of 3x plus 5 is the slope of the line 3x plus 5. And then we know how to find slope. We just look at the coefficient for x. We know that from algebra. So yeah, this is d high. So we have low d high. So I'm going to multiply by 15. 3x plus 5 to the fourth. Minus, well, you do minus because it's the quotient rule. High, the upper function, 3x plus 5 to the fifth, times d low. So we want the derivative of x squared plus 2 to the 50th. We want the derivative. Well, this one is just the chain rule again. This equals, and then we need the power rule to do that. So we bring the 50 down, multiply by the inside, subtract 1 from the exponent, multiply by the derivative of the inside. The derivative of the inside is just the derivative of x squared plus 2. And the derivative of 2 is 0 because it's a constant. And the derivative of x squared, we can use the power rule on that to just say 2x. So then we can rearrange this expression by writing 100x x squared plus 2 to the 49th. So that's the derivative of the lower function. So I'm going to write 100x x squared plus 2 to the 49th divided by all this divided by, because this is just the quotient rule, right? I'm following the quotient rule. The square of the denominator. So we'll have x squared plus 2 to the 50th squared. Okay, well, x squared plus 2 to the 50th, that's just a, or I'll call it x. This is x raised to the a power. X raised to the a raised to the b. We all know this is x to the a times b. A power raised to a power, you multiply the powers. So we're going to multiply the powers right here. 50 times 2 is just 100. So that's how you deal with the exponent. So we use this little rule right here, and then and now we can cancel some stuff. We can cancel some stuff because like we have one thing in the denominator, And we have that same thing occurring to some multiplicity in the numerator in every term. So we have like 50 of them right here, and then we have like 49 of them right here. So that means we can cancel the lower of the two numbers. We can cancel 49 of them. So all 49 of these vanish. They turn to, well, they don't vanish. They turn to 1, and you multiply 1 by anything, you get that thing out. So this just turns into 1. We don't have to worry about that anymore. And this one, we only have to subtract 49 from 50 to determine the power remaining. So this is now 50 minus 49 is 1. And then we subtract 49 from 100 because we canceled 49 of them. So that's to the 51. So I'm going to go ahead and just rewrite this. We have x squared plus 2. Well, I'll pull the 15 out front, like out here. So we have 15 x squared plus 2, 3x plus. Oh, we can do. Okay, let's just write it out. Minus. I'm gonna pull the 100x to the front, and then write 3x plus 5 to the fifth. Okay. Then we're dividing by x squared plus 2 to the 51. Okay, so we have something in this term, and then we have that same thing in the other term. In both terms, we have the same stuff. So we can pull that stuff out. We can factor. We're going to factor out the lowest. You always factor out the lowest power. So we're going to factor out 3x plus 5 to the fourth. And then, so when we factor this out, it's like dividing every term by this thing. So we're going to divide this term by 3x plus 5 to the fourth. Well, then we just have 15x squared plus 2 minus, and then we divide this term by 3x plus 5 to the fourth. This term right here. So when we divide this by 3x plus 5 to the fourth, we have 1 remaining. We have 5 minus 4. So this is 100x, 3x plus 5 to the first power now. And you can always check to see if you factored correctly by just distributing back through to both terms, to every term. And you should get, the previous line if you factored correctly. And we do that to help us simplify. So we have x squared plus 2 to the 51 still. Okay, now we can work with this. We can whatever's inside these brackets. It's nothing like to the 50th anymore. It's not like to the fourth anymore. And inside these brackets, it's only to the first power. So we can distribute this 15 through. We can distribute this 100x through, and then we'll get some like terms, and we can combine them. So this is like required for the problem. Like your professor won't want to grade your professor probably won't want to give points to if you leave it as the first step, like if you just leave it like this, because then your professor would have to look at every part and make sure it's right, and so we have to do this algebra, simplification and everything, so we can get it into a nice answer. So yeah, 15 times x squared is 15x squared. 15 times 2 is 30. And we have negative 300x squared minus 500x. All of it is still divided by x squared plus 2 to the 51. This is This is 3x plus 5 to the fourth times negative 285x squared minus 500x plus 30. Well, and this is still divided by x squared plus 2 to the 51. We can factor something. What can we factor? What could we factor? We could factor this quadratic, hopefully. I think we could. Because we could definitely factor out a 15. No, we can't factor out 15. Factor out 10 for, no, not 10. We can factor out 5. I think 5 is our greatest common factor. It's not 6. It's not 2. It's not 15. It's not 30. Okay. So I'm going to factor out a 5. I'm going to factor out a negative 5. And then 285 divided by 5. That would be 57. And then 500 divided by 5. Oh yeah, that's 100. And then 30 divided by negative 5 would be negative 6. Oh gosh. Well, hopefully you don't have to find any critical points, because that would entail setting this equal to 0. Now I'm curious, does this problem want me to factor this? Should I factor this? Can I factor this? Well, we can check if we can. If it even has like real roots. So we have b squared minus 4ac. We have 57x squared plus 100x minus 6. So this b squared minus 4ac comes from the quadratic formula. And if this is greater than 0, this is the part that's under the radical. So if this is greater than 0, then we'll have 2 real roots. So this is like A, this is like B, and this is C. Just the numbers. You don't have to do the X. It's just the number is B. And so like 57 is A. So we'll do B squared. That's 100. Well, that's 10 squared, so that's like 10,000 equals, or minus 4 times A times C. Well, this is definitely greater than 0. So we have 2 real roots. And then, so like it's factorable into like distinct linear factors. We can factor this. I don't know if it's like going to be super pretty or even like really doable, like without like doing the quadratic formula itself, which I kind of don't want to do. So maybe we can factor this 57 x squared plus 100 minus 6. We can do that. So one's positive, one's negative. The bigger one is positive. What are factors of 57? Is it 19? Yeah, 19 times 3. And then, so maybe we try 19x and 3x. And then we want the bigger one to be positive. So we got to switch these. And then 6 times 19 is our best shot. 19 times 6 is 6, 11. Is that right? Nineteen times 6. Yeah, that's right. And then, so if we put a 6 right here, then we put a 2 right here, no, 1 right here, this doesn't work as a factorization. The middle term would be like 111. So, yeah, I'm not going to worry about factoring this. I tried, but I don't think this factors nicely. Um, so then we can write our answer. I guess we just don't worry about it. Maybe we'll get like a point off or something if we don't factor this. But for the sake of time, I'm just going to go ahead and write this is the derivative of f. Does anyone have any questions? Okay. All right, now we have to take another derivative. We want derivative of f. So we need the derivative of the natural log of u prime, or yeah, so that's just the derivative of natural log of u is u prime over u. So we'll do just that. We'll divide by, this is called the argument, what's ever inside the parentheses. Oh, actually, no, we can do this a lot easier. Yeah, we'll use that trick that we saw in the PowerPoint. We can do the natural log. We can do 7 times the natural log of x plus x to the 4th minus 5 natural log 2x plus 1. Okay? Now, I kind of skipped over some finer details on that, but it was all covered in the PowerPoint. ln of x to the 7th. We can use the power rule of, this is the power rule of logs. There's a calculus power rule. But just whatever you have in the exponent just comes down, and then you multiply by the natural log of whatever else you have inside. And in this case, it's just x. So that's how you get 7x. And then the natural log of ex to the 4th. Okay, well, this is just some power, so we can bring that down. This is x to the 4th times the natural log of e. But the natural log of e is just 1, so this is x to the 4th. That's how we get x to the 4th. We subtract this one because we divide by it in the argument of f. So, and then we use the power rule on top of that. And that's how we get this one. So then we'll just differentiate that. That's going to be easier to differentiate than taking it all at once. So derivative of a constant times a function, you just write the constant and multiply by the derivative of the function. But the derivative of the function is just 1 over x, and this is like 7 over 1, so you can like multiply straight across. So then this is just 7 divided by x. That's the derivative of 7 times the natural log of x. The derivative of x to the 4th, 4x to the 3rd. The derivative of -5 natural log of 2x plus 1. So the constant, we know that just hangs out, so we can just write them on top. And then we divide by the argument. This is where we need natural log of u prime over u. So I write u in the denominator, and then I write u prime in the numerator. That's just 2. So actually it's just 10 in the numerator. And then this is the answer. We don't have to simplify any because it's like 3 separate terms. This doesn't factor in any nice way, I don't think. So now we can go on to the next problem. Linear inequality. We have 4x plus 5 plus 7 divided by 2x plus 7 plus 4x. Okay. So I'm going to distribute. So we have 12x plus 15 plus 7 is less than 6x plus 21 plus 4x. 6x plus 4x, that's 10x plus 21. So this is 12x plus 15 plus 7 is just 22. I'm going to subtract 10x from both sides. I'm going to subtract 21 from both sides. Oh, 22 minus 22. So this is 2x is less than -1. X is less than -1/2. So then the solution looks like we have a number line, we have 0, we have -1. X is less than 1/2, so it's like all this stuff. Okay, that was that problem. Let f be a function. So we're going to do this problem. Positive, negative. So we just want information about what f looks like. Well, f prime or f of x is x squared minus x minus 12. Oh. Okay. So f prime, this is differential calculus. This is calculus with derivatives. So the first step with most problems will be just take the derivative. So this is 2x minus 1. The derivative of a constant goes away, remember. Derivative of a single power of x is just the constant in front of it, and then we need the power rule right here. So we find where it equals 0, f prime of x equals 0. This is 2x minus 1 equals 0. This is x equals 1/2. So then I'll make a sign chart. Is that the next step? Or am I skipping one? Oh, this is the cut point, I guess. I call it a critical point. And then we'll make a sign chart. So we have 1/2. I can just combine it. We have a sign chart. So this is the sign chart on top. And then this is on the bottom. This is like f behavior. They're associated. So like there'll be like something will happen in the sign chart, and this will be like we have f behavior doing this. F is doing this. So the sign chart is of f prime. So f prime tells us about f. So I'll plug in random values on either side of here, this 1/2, and then we'll determine the sign of f prime. So we'll pick like 0 and 1. Just pick the easiest numbers. So we have f prime of 0 is -1. F prime of 1 is 1. So this is f prime. F prime is less than 0 in this interval, and f prime is greater than 0 in this interval. And it's going to have the same behavior throughout this interval. So you don't have to worry about checking more points. So, and then if f prime is less than 0, this means f is decreasing. If f prime is greater than 0, then this means f is increasing. So we have f decreasing, f increasing. And so look, it kind of looks like a minimum. If I put a point right here, then it's like the lowest point. So this is x is 1/2 is a minimum. Solve f prime. Solve f of x less than or equal to 0. Oh wait, the intervals on which it's positive and negative. Okay, well now we just have to do some algebra. So f of x is x squared minus x, what was it, minus 12? Yeah, minus 12. So we want to find where it's positive, where it's negative, and where it's like greater than or equal to 0. So we're going to factor it. X, negative 4, positive 3. This equals 0 if x is 4 or negative 3. So x is negative 3 and 4 give us zeros. And then it's opening upward because this is a 1 right here. 1 times x squared. 1 is positive. If this was negative 1, then it would open downward. So then the graph looks like this, with like the minimum occurring at 1/2. And so like this tells us where it's positive. F is positive on negative infinity to negative 3 union 4 to infinity, and F is less than 0, negative 3 to 4, and then F is greater than or equal to 0 on negative infinity to 3 hard bracket union 4 to infinity. That's what it was asking. Oh, no, it wasn't. This was less than or equal to 0. So this will change this answer. Yeah. So where it's less than or equal to 0, we have negative 3 to 4. You just include the 3 and the 4. So now I'm going to do a couple more problems. Well, actually, so we can calculate f double prime of this function. So like f of x is like x squared minus x minus 12. F prime of x, we already calculated this, 2x minus 1. And then we need, if we want the second derivative, then we just get 2. 2 is a positive number. So this means that f is concave upward always. And we can tell that from the graph. It looks like a soup bowl opening upwards. So this calculus we can reaffirm with what we know about quadratic functions. Okay. We have another function now. We have f of x is the natural log of x squared plus 4. Find cut points of f prime. So f prime, let's just calculate that first, right? This is differential calculus, so we have to take a derivative most of the time. So remember that the natural log of u prime is u prime over u. So then I'll just write x squared plus 4, and then I'll write the prime divided by x squared plus 4. So the derivative of x squared plus 4 in the numerator is just 2x. And this is divided by x squared plus 4 still. Okay. X squared plus 4 is greater than 0 for every real number x. So we don't have to worry about dividing by 0, and we also don't have to worry about some domain issue on the natural log. So that's good. And so now we just want to find where f prime of x equals 0. We want the x value so that f prime of that x value is 0. Well, we just say 2x over x squared plus 4 equals 0. Well, this means that we have 2x is equal to 0. And this means we have x is equal to 0. We just divide by 2. And then here we just multiplied both sides by a non-zero number. So these cancel. Then so this is the critical point. This is our cut point. So one thing, cut point is that true? Is not necessarily as a maximum or a minimum. Not necessarily a max or a min. You can have a place where the derivative is 0, but that place doesn't have a maximum or minimum. It doesn't attain a maximum or minimum value. Like the points near it, they have maybe they're like, you know, up on one side and down on the other side. So we're just like some point in the middle. And I can give you an example. If we have like x cubed, then the derivative is 3x squared. And then this equals 0 when x is equal to 0. But we know the graph of the cubic function looks like this. So at here, we don't have a max or a min, but the derivative is 0. So that's kind of weird, right? You just have to be a critical consumer of critical points. Like you could get these cut points, and then they don't actually give you a max or a min. You have to look at them before you go ahead and put them as your answer. Now that being said, this is the cut point. This is the answer. You just say this is the cut point. They probably won't differentiate between these two. These like a cut point that's not a max or a min. So you probably don't have to worry about this. But yeah, this is the thing. So what else did we want to find for this guy? Interval f is increasing, decreasing, slope chart, relative max and min. And well, there can't be both. There can only be okay, so I have to make the sign chart. So we're gonna do with 2x. So we have 2x. This f prime of x is 2x over x squared plus 4. And we have our number line. We have x is 0. And then we have the sign of f prime. So before 0, we get f prime is less than 0. Plug in like -1. Plug in +1 on the other side, we get f prime greater than 0. So this tells us f decreasing, f increasing. So once again, it's a minimum. You can just draw these arrows, and you can tell by looking at it like, oh, this looks like a min. This is a small value. So there's a local relative. This means relative. Min at x equals 0, and then of f of 0 equals the natural log of 4. Remember, f of x was just ln x squared plus 4. So if I plug in 0, that x squared goes away, and I just have ln of 4. And so this answers the last question. This is the point at which we have this minimum. This contains all the information about the min. And we want where f is positive and negative. No, it's not asking for that. But what if it asked, what if it said the natural log of x squared plus 4, where is it like greater than 0 or less than 0? So this equals 0 if x squared plus 4 is equal to 1, which never happens. It never happens because we have x squared equals -3. X is equal to imaginary number times the square root of 3, which is not a real number. So we don't have to worry about this being 0. And then it won't be less than 0 either, because like try plugging in like 1 squared plus 4. This is, well, it's not a good example. This is the natural log of 5, which is greater than 0. You can plug this in your calculator. So we have a continuous function that's greater than 0, and it never equals 0. So that means it's never less than 0. So we have like a continuous function, and it may get close to 0, but it can never cross the 0, so it can never be negative as a result, and we just have some line above the x-axis. Find higher order derivatives. We need 4 derivatives of f of x equals 3x cubed minus 4x squared plus 5x plus 12. F prime of x is 9x squared minus 8x plus 5. F double prime of x equals 18x minus 8. F triple prime of x equals 18. F, the fourth derivative, is 0. This is all just the power rule. This is just derivative of a polynomial. This is a cubic function. So any fourth derivative of a cubic function will always be 0. And then the third derivative will be a constant. You notice that like we have a cubic we start with a cubic function, and then we have a quadratic derivative, and then the second derivative is linear, and then the third derivative is constant, and then the fourth derivative is 0. So it just like knocks it down a power every time because of the power rule. Second derivative test. Is this the last question? I think it is. Okay. X squared minus 10x plus 2. X squared minus 10x plus 2. This is f. So f prime, this is differential calculus, right? We take derivatives here. 2x minus 10. And then this is second derivative test, so we're going to take 2 of them. This is 2. This is always greater than 0. So any cut point will be a minimum. So any cut point will be a minimum, and we only have one cut point. X is equal to 5. So x equals 5 is a local min. And then the x value or the y value associated would be f of 5 equals 25 minus 50 is negative 25, plus 2 is 27. So we have a minimum of 27. Is that right? That's not right. Two x minus 10.
It should be negative 23, I think.
Oh. That explains it.
Mm-hmm.
Thank you.
Yeah, of course.
Yeah, so I did all the work right, and then I just plugged in the number wrong. Yeah, because this is like 25 minus 50 plus 2. This is negative 25 plus 2. This is negative 23. Yeah. Okay. Well, that's all we have for the problems for today, guys.